Okay, today's topic is graphs of sine and cosine. So I want to start with the basic graphs of just regular old sine and regular old cosine, and then I want to talk to you about translating those graphs. So moving them around, sliding them, stretching them, squishing them, all that sort of stuff. So let's just start with a regular graph of y equals sine. What this is about is basically translating the circular motion from around the unit circle into a xy graph. And here's a cool little demonstration of that Mr. Kistner found online. If you watch um, this motion around the circle, if you were to graph the height of the dot, it this demonstration shows how it creates this little wave pattern. At every time period or every angle that we've gone around the circle, if you graph the dot, it's easier to watch than it is to explain in words, but you can see how this circular motion translates into the a graph like we're used to, an x and a y graph. So what we're going to do is pick some points, figure out what the sine is of those angles, and then we will end up with a wavy graph like that was. So let's just start at 0. The sine of 0, sine, remember, is your height. So when we start at 0, our height is 0 right here. I don't have any height because this is my x-axis, meaning my height is, I don't have any. So that means the sine of 0 is 0. Now as you start to move counterclockwise around the unit circle, when you get to, when you get to 45 degrees, when you get to 30 degrees, you have a sine of 1/2. And when you get to 45 degrees, you have a sine of square root of 2 over 2. Some of those points are convenient to graph, and some of them aren't. Let's make this 1 and this -1. At 30 degrees, which is about right here, I'm up to a half. My next real good landmark is when I get to 90 degrees. When I reach the top of the unit circle, my sine up here is equal to 1. So at 90, your height should be 1. All right, and then you start moving back down. As you move across this way, it's slowly at first, but your height starts to drop, and then it starts to drop faster and faster until you get to pi, where your height is back down to 0. And I should say 180 degrees instead of pi. There were spots along the way, but we don't need to put them all. We just need some good landmark points. When you get to 270, your height is all the way down to -1. When you get to 360, it's back to 0. So you can see this motion, how it translates from circular motion into this sine wave by just basically every 90 degrees, you go from the axis up or down, and then back to the axis, and then up, and then back to the axis, and so on. And then, as neatly as you can, you connect these with a nice wavy graph. Right? Some of you, the artistic ones, will enjoy some of this graphing. Some of you will make really jagged waves. It's all right. You just get the landmarks on there and do the best you can with the picture. So this graph illustrates an important idea about sine and cosine. Sine and cosine's whole universe is between +1 and -1. So unless we multiply it by some constant, a sine wave is going to live in this little world between -1 and 1 because it's generated by the unit circle. So your unit circle never goes further left or right or up or down than 1, so therefore this graph only exists between -1 and 1. Okay? So let me show you that one more time so you can just kind of get another good visual of this circular motion turning into the graph that we've just made. All right? I thought that was a pretty cool demonstration. As far as your notes go, just get a pretty decent sketch of this sine graph. You don't have to draw the whole unit circle every time. But notice this was sine of theta, meaning degrees. For our cosine graph, we're going to graph y equals the cosine of x, which means x indicates radians. There's not much difference here, except instead of saying 90 degrees, I'm going to say pi over 2, and instead of saying 180 degrees, I'm going to say pi, and so on. The only other difference is that our graph is going to be offset by 90 degrees. Your sine graph started at 0, right here, that little 0 right there. Your cosine graph is actually going to start at 1 because at 0 radians or 0 degrees, the xy-ness of your graph is at its maximum value. You don't get any further to the right than you do right at the starting point. So cosine starts right there. By the time we get up to pi over 2, your rightness, your left to rightness, has been at its maximum value, and it starts to creep back down. And when we get up here, your cosine is 0 because you are on the y-axis. So pi over 2, we're back to right in the middle, left to right speaking. When you get over to pi, which is on the far western side, if you see what I mean, you're at your furthest left. 3 pi over 2, the bottom of the circle, you're back to the middle, and so on and so forth. And then going the other way, you can just keep the pattern going. The fact that this graph goes left and right just illustrates that you can go around the unit circle backwards as well. All right, and again, the best you can. Oh, I missed a spot right there. That's no good. And there's a graph of cosine x. Remember, x because we're talking radians. Okay, so the sine wave is kind of interesting. It would just be, let me clone that and turn it blue. The sine wave would just be your cosine wave offset by 90 degrees. So it would go like that. I might need another couple clones to finish off the pattern. It's not going to be perfect, but you get the idea. So there's a sine wave set on top of a cosine wave, and it's just the same wave existing between -1 and 1, and it just happens to be starting at 0 instead of starting up at 1 the way cosine does. Both of them still live only in this little world between -1 and 1. So there are your basics. Here's really our goal. I want to be able to give you a function like this and tell you to graph that. So there are 4 numbers that have been thrown into the mix. Number 1, this +3, and if you remember any of our translations, a +3 in that spot should just move the entire graph up 3. So originally the x-axis is what's called our sinusoidal axis. Our new sinusoidal axis, or our new ground level, is going to be up 3. Get that word on so you can write that down. Which means at 3, we're going to have our new sort of ground level. You can just indicate that with a dashed line or a light line. It's not part of the graph. It's just we've moved our, what used to be laying on the x-axis, we moved that up 3. Next change. This 4, the number that comes before the cosine, is called the amplitude. Amplitude, you might have talked about this in some science classes, is a measurement of how far up and down the little peaks and valleys go. It's not a measurement from the top of the waves to the bottom of the waves. It goes 4 in both directions. So since we moved up 3 and we have an amplitude of 4, from this new ground level we're going to go up to 7. This is sort of like it's exactly like a vertical stretch from when we were talking about translations. And we're going to go down 4 to -1. So this is the new world in which our graph's going to live. It used to be down here between 1 and -1, but we moved it up and we stretched it so that its base level is up 3 and its amplitude is now 4, so the whole thing goes from top to bottom a distance of 8. Let me get rid of those. Okay, so what other changes do we have to worry about? A horizontal shrink or stretch is going to change what we call the period of the graph. To find the new period of the graph, you take 360, which was the original period of the graph, and you divide it by that number that's right in front of the parentheses. The period is how long it takes for your graph to make a full revolution and start repeating itself. So the period of a regular sine or cosine graph is going to be 360 or 2 pi because this distance right here is when you know, our starting point and our finishing point. We get right back to where we started. It's not here because we're on the way down, so that's not the same thing. It's when you complete a full revolution around the unit circle and you start from scratch. So back to our current problem. The period is originally 360, and like I said, if it's in radians, you're going to do 2 pi where that 360 is. But you divide it by that number to figure out your horizontal shrink and stretch. So what this means is that 72 degrees is our new period, which means it's only going to take 72 instead of 360 to do its full wave up, down, and back up to the starting point. Actually, this is cosine, so it's going to start at the top and go down and all the way back up, which means what we're going to have is a squished up cosine graph with a lot of squiggles instead of big, long squiggles. We'll get to that in just a minute. First, this last one. This last one, a negative 10, means that we need to shift the entire thing 10 in a certain direction. And again, recall from our translation days, and a horizontal shift is the opposite of what it looks like it should be. A negative 10 looks like it should go to the left, but we're actually going to go right 10. You know, in the same way that x minus 2 squared is a parabola that's been shifted to the right 2, this is a cosine graph that's been shifted to the right 10. Let me get rid of that parabola talk, and let's graph. All right, so to draw your graph, start with the new sinusoidal axis, which I've already drawn. Then use your amplitude to get your top and your bottom cutoff points. Those are like walls that your graph can never go past. Next, take the original point where a cosine graph would start, which would be at the top, because cosine starts out at 1 on our original cosine graph, and shift it to its new starting point, which for us is right 10 degrees. So that point, that's where I'm going to erase that one so I can show you the new one. That's where cosine would start. I'm going to start it about right here at 10 degrees. Okay, so there's our right shift of 10. Now, you use the period of 72 to determine when you're going to complete one full revolution. So if I'm starting at 10, that means my revolution needs to be done 72 degrees away from there, which is going to be right here at 82 degrees. So I maybe should have rescaled my axis before I started this, but this will really illustrate the fact that this is a squished up graph. So one full revolution of the graph later, I'm right back up there, 72 later. So 36 would be a half of a period. So if I'm starting at 10, by the time I get to 46, that blue line is 45, so 46 is basically right there. At 46 degrees, I'm down at the bottom. And halfway in between there, I would be on the axis. Okay, 72 later, let's see, if I'm at 82 and I add 72, that's 154, and it's kind of difficult to, on this scale, I really should have rescaled, but let's say 154 is somewhere in here. That's another full revolution, and halfway between there, those two, I'm down back at the bottom again. Okay, so what I end up with, and I should do, usually the question asks you for 2 full revolutions at least on your graph. I'm going to add in a couple more reference points. And what we end up with is this really tall, I'm not doing a great job here, it shouldn't go back and forth like that. It basically looks like that. So, not the prettiest, but there's a sine graph. So remember those 4 translations, your sinusoidal axis, your amplitude, your new period, and your left to right sliding. All right, so there's a graph. We'll do more of these in class, and I will see you then. This is Broseph Gwibbles, and I'm out.